And we're back. Alright, so we were finding, using method of joints to find the member forces in each of these parts. We set up first with joint B, I should label this, joint B. We had to break up FBA into two components. We set up some of the forces in the x direction equal to 0, got an equation for that, set up the forces in the y equals 0, eventually found BA to be 375, plugged that back in over here for BC to be 300. So now we need one last member force, and we're going to take a look at, if I can scoot this over just a little bit, joint. Now it doesn't matter which we pick. We could pick A or we could pick C. I'm going to go ahead and pick C only because if I do, FBC is already in a horizontal direction, and it's one less component I'll have to break, one less force I'll have to break into components. So this is joint C. So if we look at that, again, draw our free body diagram. We have a reaction force, Cy, that we know to be 720 pounds. We have FBC, which we knew was in tension, so FBC we found to be 300 pounds. And then we have FAC, which is what we'll eventually try to find, which is at some angle we don't know at this point, and we'll have to break that into components. But this is what we're trying to find. It's the only thing left that we don't know. So let's try to do that. Now, in the same way we use the sides of a triangle to find the sine and cosine of this angle, we could do that. If you wanted to, you could find that actual angle by saying the tangent of that angle theta, let's say if this is angle theta, is opposite over adjacent, or 9 divided by 3.75. If you do that, you should be able to do theta equals to inverse tangent of 9 over 3.75 and work that out in your calculator. Now I'm using the computer calculator, so I don't have an inverse tangent function. I'll do it a different way. So FACX is going to be equal to FAC cosine theta, because I'm setting up my theta so that the x direction is along the adjacent side, adjacent over hypotenuse. But in this case, well, I need to find what that hypotenuse is. So I use Pythagorean's theorem, a squared b squared c squared, so that the height here, 9 feet, or 81, plus my base is 3.75 in this case. 3.75 times 3.75, close parentheses, add those two up, I get 95.06, square root of that, I get 9.75. Alright, so this side, what I just did, find out that this side is 9.75 feet, just by looking at Pythagorean's theorem, a squared b squared c squared. So now that I know that, I can apply that, because I need the cosine of theta, adjacent over hypotenuse. The adjacent is 3.75, hypotenuse is 9.75, so FAC times, what did I say, adjacent, 3.75 over 9.75, and let me shut that off real quick, over 9.75. So if I divide that out, get, bear with me a sec, 0.38 something something something. So 0.38, I'll take it out 4 decimals, 46. That's more than enough. FAC, and that's again FACX. That's a component in that direction. And in the same way, we might as well, actually I'm not going to find the y component, and you'll see why momentarily. We're only going to need to set up only one equation. So let's set up, since I did the x component, sum of the forces in the x equal to 0, our old friend the equilibrium equation. What forces do I have in the x direction? I have FBC and a component of FAC, the x component. So FBC plus FACX have to be equal to 0. Now I have a value for FACBX, well not a value, but an expression, 0.3846. I could have kept a fraction in here too if I wanted to be exact. FAC equal to 0. Now I know FBC, I calculated that over here. So 0.3846 FAC is equal to negative FBC. I just moved it from one side to the other. FAC is equal to the negative 300 pounds that we found FBC to be, divided by all that mess, 0.3846. Look, I kept that in my calculator, so I can just divide that out. So let's see, divided by 300, and then flip that over. I should get FAC equal to 780 newtons. Nope, sorry, pounds. Thinking physics. 780 pounds. The fact that it came out positive means it is in tension. Great. So I have FBC, I have FBA, and I have FAC. I have all three member forces by doing the same equilibrium equations, just applying it to the joint itself.